Jai Hind everyone. I Neeraj Sharma, Assistant Professor at Ajay Kumar Garg Engineering College, Ghaziabad. I am working in the Department of Electronics and Communication Engineering, where I am teaching final year subject Microwave and Radar Engineering, whose code is KEC 074 from the AKTU curriculum. This is my first video lecture for the complex video lecture series. So the topic which I have chosen this time for this video, that is the generalized solution of wave equation in rectangular waveguide. So mainly we know that we are using the rectangular waveguide for the purpose of the wave propagation at the microwave frequency. So how these wave generally we can see how it is, we are not able to view it how it is traveling, but we can make some theoretical study regarding this if we will able to find out the value of E and H in the waveguide with reference to some value, so that we can say that if we are getting any value for the electric or magnetic field component, then we can say that the wave is propagating inside that waveguide. So in this I have just chosen the topic this one, so where just simply I am this one is in a rectangular waveguide for just reference. Just a minute. This is a rectangular waveguide, as you can see here, where we are using the rectangular coordinate system because it is having the some waveguide having the length A and width B, and the wave is propagating into the Z direction. So when the wave is propagating inside the Z direction, so we have to calculate the value for the electric and the magnetic field inside this rectangular waveguide. So for that point of view, we are just considering the electric and magnetic field equations are given by del square E is equals to minus of omega square mu epsilon into E. This is the Helmholtz equation for the wave propagation inside a waveguide. So let's say consider gamma square is equals to of minus of omega square mu epsilon. So this value will become del square E is equals to gamma square into E, and similarly for magnetic field we can write it like that, del square H is equals to gamma square of H. So this will be the value for the electric and the magnetic field equation. So the scalar to satisfy this E or H, rectangular components of E or H satisfy the scalar wave equation or Helmholtz equation. So we can, so the scalar wave or Helmholtz equation is given by, let's say, del square psi is equals to gamma square of into psi here. Let's say this one is equation number 1, it is equation number 2, and let's say this will be the equation number A. So now this will be a generalized equation that we are using, which can satisfy variable we have considered here, del square psi is equals to gamma square into psi, and this gamma may be valid for E, satisfy the condition of E electric field as well as the magnetic field here. So now we can expand this equation according to the rectangular coordinate system. So now expand equation A in rectangular coordinate system. So we can write it like del square psi over del x square plus del square psi over del y square plus del square psi over del z square is equals to gamma square into psi here. So this equation, as you can see, the expansion of this equation A, del square psi, this one. So now we can see that this is the equation of the second order equation, and now by the help we can able to solve this equation with the help of separation of the method of variable. So we want the solution. If we get the solution of this psi, which will be the solution of this our topic wave equation solution. So we are interested here to calculate the find out the value of this psi variable here, which is satisfy the e value for e as well as for h also. So here we can see that this will be the second order equation. It will have the solution. We can solve this second order differential equation with the help of method of separation variable. So by method of separation of variable, so the solution is assumed. So the solution is assumed as psi is equals to x of x, y of y, z of z. Let's say this will be the equation of B. So the solution of this A equation will consist in the form of psi is equals to x of x, y of y, z of z, which is given as the equation number B. So in this, what we can do, this variable consists of rectangular coordinate system coordinates. So where this x of x, if we think this x of x is a pure function of x coordinate only. Similarly, this y of y is a pure function of y only, y coordinate. Similarly, z is the pure function of z coordinate only. So that means these three variables, x of x, y of y and z of z is a pure totally independent with each other. So now we can find the solution. So we can now put the value of equation B into equation A. So what we will get, we can get the value like this, yz into d square x over dx square. Just a minute. Next one is xz d square y over dy square plus xy into d square z over dz square is equals to gamma square. Also we can put the value here x, y, z. Now we can also simplify this. So we can write it like this, 1 upon x d square x over dx square plus 1 upon y d square y over dy square plus 1 upon z d square z upon dz square is equals to of gamma square. So we can now write like this. We can write this equation in this form. This is the solution of for the equation of A. Now after that the left hand side we can see here this LHS of this, let's say equation number C, having the three variables. This is the sum of the three variable which are the constant here, and each term, these three, 1 upon x d square x, 1 upon y d square y plus dy square plus 1 upon this 1 upon z d square z over d z square. These three are the independent variables here. Okay, so and the solution is the sum of all these three. So now we can consider all the three as a different variables. So now we can all are the, these three are the constant. First thing. Okay, so now we can, and each term we can now named as an k x square, k y square and k z square. So now we can write here like 1 upon x d square x minus sorry this one. So 1 upon x d square x we can now write it here minus of k x square minus of k y square minus of k z square is equals to of gamma square. So we can now write the equation C in this form. Let's say it will be the equation number D. So the general solution of each differential equations we can now write it like this. So for first one, let's say d square x upon dx square is equals to minus of k x square into x. First part for this one only. Second one this is the now third one. So this one this will be the equation. Now we can consider, because and easily we can assume because all the threes are independent and this equation having only the function of x only. So the solution, when we will find out the solution of this differential equation using the CF and PI complementary function and particular integral methodology. So here just we are applying the approach complementary function. So we can see here d square plus m square equals to 0. So this will comes out d here we can root get the for the x is equals to plus minus of kx. So we can the solution plus minus j kx. So this will be the imaginary component. So the solution for this in terms of x will comes out, let's say a, we can now consider it a sine k x into x plus b cos k x into x. Okay. Similarly for d square y over dy square we can y is equals to c sin k y into y plus d cos k y into y. Similarly for this third one we can write it like this: d square z upon d z square is equals to minus of k z square z. So the solution for this z equation for this variable z will comes out as from the CF and PI. This will be comes out E sin k z into z plus f cos k z into z. So these three variables now we can find out here. So the total solution of this equation B will comes out psi is equals to A sin kx into x plus B cos kx into x, C sin ky into y plus D cos ky into y, and the E sin k z into z plus f cos k z into z. So this will be the solution of this equation for the psi by the method of separation of variable. Now after that, when we will consider here, so we can find that the wave is propagating in the guide is assumed in the positive z direction. The waveguide is propagating in the positive z direction. Okay, so so the propagation constant gamma g, the propagation constant, total propagation constant gamma g will differ from the propagation constant of the dielectric. So that means we can now let gamma g square is equals to of gamma square plus we can write it like this, k x square plus k y square. Okay, where and also we can now write it again, we can change it and write gamma g square is equals to what, gamma square plus kc square, where this kc is equals to under root of this kx square plus ky square, that is the cutoff wave number. This is wave number, which will shows the half wave variation along the respective coordinate. Okay. So after that we can now write it gamma g is equals to what, this we can consider here gamma g square is equal to gamma square plus kc square. So we can now write it gamma g is equals to plus minus of under root of omega square mu epsilon minus of kc square. How we can write it like this, because of gamma square. Now we can conclude this as an this one, because of here gamma square is equals to minus the omega square mu epsilon. So as per this condition, which we can see here, as you can see here, gamma g is equals to plus minus of under root omega square mu epsilon minus of kc square, and this gamma g will contain the alpha g plus j beta g. This will be the this gamma g propagation constant of complete guide having the attenuation constant real part alpha g as well as the imaginary part in terms of phase constant, that is the beta g. So the wave should be propagate inside the waveguide, it should be depending upon to this factor of imaginary factor. So for that point of view, in this equation the three case will be discussed, we can discuss here. So the case 1, first case, now we have to consider here, that is the omega square mu epsilon is equals to of kc square. This one, if both are equal, then in this condition gamma g is equals to what, 0, gamma g will become 0. So this type of condition when arrives, so this will be known as the cutoff condition. Means in this condition no wave will propagate, neither propagate nor attenuate. So at this time the frequency will named as a cutoff frequency fc, which is given by fc is equals to 1 upon 2 pi under root of mu epsilon under root of this kx square plus ky square. Another case 2 we can discuss here, that is the if omega square mu epsilon is greater than kc square. So what will happen if this value is greater than, this part is greater than kc square, so the overall part will be positive. If omega square mu epsilon is greater than kc square, so the final solution this part will be positive. So under root of we can solve, so the gamma g will comes out the in terms of imaginary part we can get here the solution in the form of solution, we will get only this imaginary part, that means phase constant. That means what? So omega g will comes out this one, it will, we can write it like plus minus of j omega under root of mu epsilon under root of 1 minus fc upon f square. So in this condition this wave have this only the imaginary part, so that the wave will propagate. So in this condition the wave will propagate. Now case 3, if omega square mu epsilon is less than kc square, so in this condition the in this condition when we will consider this part is positive, so the result you can get omega g is equals to of alpha g, and this value will comes out plus minus of omega under root of mu epsilon into under root of fc by f square minus 1. So in this condition this will having the only the real part, the wave will attenuation constant. So in this condition the wave will attenuate and the wave will decrease exponentially with the factor of alpha g. So in this case, by concluding, if we will conclude the 3 points case in this equation for the frequency, let's say for this, let's say we will consider the cutoff condition, that means this condition we are considering here, the wave will not either propagate, neither propagate nor attenuate. So if f, so as you can see this, if in this condition, only in this condition, that means f is greater than fc, the wave will propagate, that means ki from this point the wave will propagate. But in this condition when the f is less than fc, that means this part wave will not propagate, that means attenuate. So this graph will show the similarity of the wave propagation inside the waveguide like on a half high pass filter. So we can also conclude that the waveguide acts as a high pass filter here. So the after considering all these 3 conditions and the solution of this wave, which we can get here this one by this equation. So we can now conclude in the form of wave propagation, we can write here the solution of xi is equals to a sin k x into x plus b cos k x into x plus c sin k y into y plus d cos k y into y, and the wave we are assumed that the propagating in the positive z direction with the propagate phase constant of beta g e raised to power of minus of j beta g into z. So this will be the generalized solution for the wave equation inside a rectangular waveguide. So on the basis of this solution which we can get in last, so we can, after using this value of psi, we can also solve the value of E as well as electric field. We can now calculate for in TE mode as well as in the TM mode inside a waveguide. So now this is the from my side. Thank you. And the reference book I have chosen here, this is the Samuel Y. Liao. So thank you and Jai Hind.